professor at IISc Bangalore in 1996 to 2002. He has worked as a lecturer at Cornell University, USA during 1994 to 1996. Among other research interests, he works in the field of micro-electromechanical systems and currently heads India's first research lab in the field of MEMS, the Crane Sky MEMS Lab at Indian Institute of Science, Bangalore. His book on MATLAB, Getting Started with MATLAB 7, is popular among the students of engineering. He is also the chair for the Center of Nanoscience and Engineering SENSE. Dr. Rudra Pratap sir is an associate editor of Shock and Vibration Journal, which publishes articles on various aspects of shocks and vibration, including vibration measurements, vibration conditional monitoring, shock hardening, fluid structure interaction, impact biodynamics, vehicle dynamics, and gun dynamics. He has published more than 104 journal papers, 120 conference papers, and taken several seminars. He has 7 patents to his name. We welcome you, sir. The session is all yours.
Thank you. Um, I don't know where you got all that introduction from. That is somewhat old. Anyway, it doesn't matter. I'm so glad to be here. I thank Dr. Kiran Bhole for inviting me to this this FDP program on MEMS. Nothing makes me happier than talking about MEMS. Just before coming to this lecture, 3 minutes before this, I was giving a lecture in another FDP program, another program in Jalandhar on MATLAB computations. So I just got 3 minutes break to come to this. Anyway, all the participants also, I heard they just got a couple of minutes of break, so it's even. Let's talk about MEMS transducers. Okay, that's what the topic is for me to talk about today. I am logged in from Indian Institute of Science. For those of you who have never been here, this is the main building. We have a beautiful green campus here at IISc. And I just love this campus. It's so beautiful, so green. You can see here, just 1 second, let me use pointer options, laser pointer, so that you can see. Yeah, this is a fairly big campus, 450 acres or so. And inside, you can see that, the green part is right here, and just outside the compound, it's all concrete jungle. You can see that. So we have a beautiful green campus, and in this campus, this is where Center for Nanoscience and Engineering is located, which I was instrumental in building, in making. It came into existence in 2010. The picture I showed you of main building is right here. Okay, so this is our Center for Nanoscience and Engineering, where we do lot of MEMS related work and nanoelectronics related work. The center has the biggest or the most attractive part of this center is this nanofabrication facility that we have. It's a huge facility, 14,000 square feet clean room facility that we have inside. We built this facility with almost 150 crore investment in it. And this facility today serves the entire country. About 700 institutions, universities, institutes, research labs use this facility. When I say 700 institutions use this facility, mostly it's PhD students from these institutions and assistant professors, the younger researchers who want to do hands-on work. They come here and use this facility. There is a program called Indian Nanoelectronics Users Program, under which you can get access here, and all expenses are paid through that program. That's how most researchers have come here and used this facility. Almost 500 PhD theses of other institutions PhD students have completed their thesis at the center. Uh, and of course we have lots of students of IISc itself, 150 PhD students of the center alone who work here, and many more students from IISc from outside the center, but different departments. They also use this facility. So this is a facility which is open for usage, but everybody has to pay, including me. Although we spent 10 years of our life building it, but we all pay for usage. Whatever tools you want to use, there is per hour charge. You use it and you pay. So now let's, that's in the background where all of the things that I'm going to show you are done here. Okay. So now let me just give you the outline of what I'm going to cover. Uh, First, we are going to talk about transduction because this talk is about MEMS transducers. So we'll talk about transduction first, and then I'll tell you why these MEMS transducers have become so important in today's world, because we are looking for imparting smartness to everything that we make. Okay, we want to make everything intelligent, whether it's our cell phone or computers or our chairs and desks or walls and houses and washing machines or whatever it is. We want to impart certain intelligence to all of them. So what does that mean? What is its relationship with transducers? Where is MEMS transducer technology today? And then I'll give you some examples of modern transducers or sensors. And then, we'll see some examples of inertial sensors, acoustic transducers, optomechanical transducers, and then conclude. So transducers are all about transducing one form of energy into another form of energy, right? So if you think about some sort of mechanical energy being converted into electrical energy in terms of a signal, as I speak, um, I have mechanical energy propagating in the air, which is in terms of acoustic pressure, right? And the microphone in this cell phone, in this computer, in my laptop, which is picking up this mechanical energy, is converting it into an electrical signal, which is then getting transmitted to wherever you are, to your computer. And then your computer is taking that electrical signal through its speakers and converting it back into mechanical energy and actuating a diaphragm to produce the sound that you are able to hear, right? So from mechanical energy to electrical energy, generally, when we go like this, it doesn't have to be mechanical energy. It can be chemical energy. It can be some other form of energy. And you transfer to electrical energy. That's generally what we call sensors. And, when we take electrical input and convert it back into useful work or, some other mechanical signal, then that's actuator. And this word of actuators and sensors is what uh, is the constituent of transducers, right? Transducers, both are transducers, sensors and actuators are all transducers. So when you want to work, if you want to work in this area, then obviously whatever energy domain is of interest to you here, you have to be good at that energy domain, good at handling that energy domain. So for example, if it is mechanical energy, then you must know about displacement, velocity, acceleration, force, pressure, temperature. These kinds of variables should be sort of second nature to you. You should be able to think in terms of equations for these variables, in terms of how to measure them, how to use them. And similarly for electrical, you will have current, voltage, capacitance, resistance, inductance, these kinds of variables that you must know, right? So if we want to work in these areas, then we have to be very comfortable with these kinds of variables, And that's what, uh, you know, working in these areas requires, right? That you have a certain amount of expertise and comfort with these domains. So let us see for just in a black box approach what sensing is like. How does it work? What sensing is all about? So you have some sort of a stimulus. This is, let's say this is mechanical stimulus, could be pressure, right? Or could be acceleration, could be something, some mechanical stimulus. Now this is coming onto a black box which you call sensor, right? So it's on this sensor, and sensor gives you a signal which you can record, which you can log, which you can transmit. This is what you want to do with sensors, right? Take a stimulus, convert it into a signal which is recordable or loggable or transmittable, or all of those things. This is what sensors do. How do they do that? So you have inside this black box, you have some structure which responds to this stimulus. It responds to this stimulus, and then that response, that mechanical response, you are able to transduce through some transduction technique into the signal that you want to record, or you want to translate into this signal, right? So if this is electrical signal, then this mechanical response has to be translated into an electrical response somehow. And what that somehow is what is called transduction, right? So let us, as I gave you the example of the microphone and the speaker, what does a microphone do? It takes acoustic pressure, right, and converts into electrical signal. If this is the kind of electrical, the pressure, acoustic pressure that is coming as an input on this diaphragm, the microphones have a diaphragm. The diaphragm vibrates in response to this dynamic pressure. So this is time versus pressure. You have some signal coming. This is vibrating. And just imagine that if this is a conductor, this diaphragm is a conductor, or that there is a conducting surface on it. And then in the back side also you have another conductor, so that you can form a parallel plate capacitor between the two. Now, this plate as it vibrates, this diaphragm as it vibrates, that one plate of the capacitor is moving, and the distance between the two parallel plates is changing. Obviously, that will change the capacitance, and therefore it will change the voltage in the circuit in which this capacitor is embedded. And then you get voltage versus time graph, right? So that's your electrical signal. So if you use a capacitor in which one part of it is mechanically deforming, then you got a transduction mechanism that is changing mechanical energy into electrical energy, and that gives you this kind of this microphone. So this transduction can be done in many ways. You could do capacitive transduction, piezoelectric, piezoresistive, optical, electromagnetic, thermoelectric, piezoelectric, photoelectric, photoelastic. There are many, many, many transduction mechanisms, right? And this is something that we have discovered over centuries by working on different materials. This is nature's gift to humanity, that you have all kinds of materials that do this transduction, take one form of energy and change it into another form of energy. And that's what we use for designing transducers, right? Depending on what kind of transducer you're designing, you choose one of these transduction mechanisms and you use it to your advantage. Now let's look at transducers and smartness, or what I call the foundations for ubiquitous intelligence that we want to impart to everything that we design and make today, right? That's what our quest seems to be. For a while, it was about information. Now information is ubiquitous. It's everywhere. It's at your fingertips, right? Any information you need, you can get that information. So similarly, we want now a bit of intelligence everywhere, So what is that intelligence or smartness? What does that mean? Now, smartness comes from sensing. You sense things, you think about it, and then you act on that. This is what you will call intelligence. Sense, think, act. That's what intelligence is all about. Okay. If there is no input, what are you thinking about? What will you think about? So there has to be something to think about, and that comes from the input. When you are looking at this screen, there is sensing of the screen, that there is information on the screen. That's what you are thinking about. And then you are acting. You are saying either that, okay, I don't want to listen to this guy, I want to go and have a cup of tea, or you are saying, okay, whatever he is saying makes sense, let me listen to him a little more. There is decision being made continuously. So sense, think, act, these are the three pillars of smartness. In terms of now man-made intelligence, what does that translate to? It translates to sensors, processors, and actuators, right? Sensors for sensing, processors for thinking or for processing the information, and then decision making, and then actually translating that decision into actionable items through actuators, right? So that's what man-made intelligence is. And this is what we want to embed in everything possible. Now, on the processor part, we are very well covered. Processors are today very, very small, and they are so readily available. There are hundreds of different kinds of processors, including many that digital signal processors, or RISC processors, uh, for doing all kinds of instructions. So this is very well covered today. Sensors and actuators at the same scale is where all our current emphasis is. That can we make sensors and actuators at the same small scale so that we can build intelligence into tiny packets, and those tiny packets can be attached to anything, you know, anything that we make, and we can impart into it. So where do we get inspiration for this small scale intelligence, or small scale packages of sensors, processors, and actuators? Look, this is probably the smallest insect that we know, a fairy fly. You know, from head to toe, it's just 200 micrometers. That's it, 200 micrometers. All sensors, all processors, all actuators for its survival are embedded in this 200 micrometers. Imagine that, you know. This is incredible engineering, but it's done by nature. Unfortunately, we don't have access to those engineering tools that nature uses and those manufacturing tools that nature uses, right? But nevertheless, it's worth looking at this as an inspiration, that how does it do that in such a small package, right? And it's not just that, this 200 microns, right? All of you know that a single hair diameter is roughly about 100 microns. So this insect is so small, and this insect goes, hunts for food, lays eggs, nurtures its eggs, brings out babies. All of that is done at that scale. It's just astounding, right? So obviously it is possible to build sensors, process actuators, which are very, very small, in full glory. This is a beautiful picture that I like of this insect, right? And you can see almost that, these hair-like structures, which are sensors at the end of its wing, with which it tries to find out temperature and, hardness inside pores of leaves where it wants to lay eggs, right? This is already at at the extreme of the usual photolithography. Now, I'm not talking about extreme UV photolithography, but I'm talking about the lithography that we do. 1 micron is what you get from there, or if you do all kinds of acrobatics, you probably get 0.9 microns or 0.8 microns, but that's about it, right? So this is already at that edge, right? And this is made by nature. So nature's package systems, look at, so here is the fairy fly that I just showed you, right? Uh, a tiny insect, 0.2 mm, right? 200 microns. Multiply it 10 times, you get a fruit fly, which is 2 to 3 millimeters long. And that has far more sensors, right? You know, it has something like 600 sensors just for smell. And then you get to honeybee, which is 10 times bigger, and now you get many more sensors here, and even in the processor, the number of neurons it has are much larger, right? So you get this kind of scaling in nature, and you want to learn from that scaling, that how is nature scaling these objects, how is it scaling the intelligence and associated machinery, right? How many sensors do they use? What are the transduction schemes they use? We don't know all of that. What we know is what we carry with us today, and we call it a smartphone. This is the evolution of the smartphone, right? You know, starting from the usual phone to not so smartphones, but cell phones, and then finally it arrived in this form, and we call it smartphone. Why is it smart? What is so smart about it? What is so smart about it is that it has sensors inside it, right? It has sensors that sense vibrations, sense rotation, sense motion, sense light. It has several sensors built into it, and that's what has made it smart. I don't know about you, but I first time when I saw my, the cell phone I got, and I saw when I rotated its screen, or the rotated the cell phone, the screen rotated. That's when I noticed first time. I said, well, that's pretty smart. So that was smartness to me. But how does that happen? That happens because inside there is a gyro, and that gyro tells the cell phone that, hey, your screen has rotated by 90 degrees, and you better rotate all the displays that you have also by 90 degrees. And obviously then it is smart, right? So currently there are about 10, in that ballpark figure, 10, 15, 20 sensors that these cell phones are using. Do you notice that cell phones today advertise, on TV for everything other than their phone functionality? Do you ever hear nowadays that the cell phone is advertising for, you know, how clear the sound is, or that it is able to transmit sound? No, it's selling for cameras, right? It is selling for, your keeping track of your health. So all of that is just based on how many sensors we are using. So today it's 10 to 20. Going forward, within 5 years, we will have 100 sensors in these cell phones. That's how this whole area is changing. You could have a smart glass which has all kinds of sensors built into it, all kinds of transducers built into it. It doesn't have to be a dumb spectacle that it is right now, occupying so much of real estate on your face and doing just one function. um, your clothes could have transducers in them. Your shoes, your jewelry, your watch has already so many transducers in it. So now you could be wired with almost, going forward, the projection is that you will be wearing 1,000 transducers you will have, right, in different forms. And you wouldn't know that you are wearing 1,000 transducers. It's not like you have to put 1,000 of them on your body, but it will be embedded in different things that you use, right? Smart home will need far more, and then home is inside the city. City will require a lot more sensors and transducers. So going forward, you are looking at incredible explosion of use of transducers. So the forecast is that by 2032, we will be using about 45 trillion sensors, right? The world will require 45 trillion sensors. This is called trillion sensor vision. This came from a meeting in 2013, and an amazing growth of transducers is going to take place. So obviously, if you are going to be using trillions of sensors, it can't be the usual sensors that you use. It has to be very small MEMS scale sensors. So let's get back to MEMS transducers. Okay. In MEMS transducers, typically we use these four transduction schemes: capacitive, piezoelectric, piezoresistive, optical. These are very popular in MEMS transducers. Not that you cannot use other transduction schemes, you can, but at least till now, we have developed technologies of how to exploit these transduction schemes, right? For example, if you take capacitive sensing, it just starts with that parallel plate capacitor. All of us know that C is equal to epsilon 0 A by D. This is A is the area of the plate, D is the separation between the two, epsilon 0 is the permittivity of space here, or the dielectric that we use here, and C is capacitance. Now, if you have something like this, uh, if you change the distance between the two, the capacitance will change, right? Delta C will be the original capacitance minus the capacitance that you get after you move this plate by a tiny amount X, right? Now, if you take the ratio of the two, then you get a pure play function here on the other side, which is just a function of X, which means that you should be able to find out what the displacement is just from the change in capacitance. And if you can find what the displacement is, you can figure out lots of things, right? That displacement could be time-dependent displacement. You could find velocity, you could find acceleration, you could find force. All of those associated variables or stimuli you can find just from finding X, right? So you can exploit this for building sensors, and that's what you do in excuse me, touch screen, right? Touch screen sensors are precisely that. You have you have a screen which, if you touch, it has a flexible membrane on top, and when you touch, it flexes, and behind that there are electrodes, arrays of electrodes, and wherever you have touched, at that point the capacitance has changed, and that's what you get into your system as a signal, from which you figure out that which coordinate, at which point somebody has touched, and that corresponds to what key or command or whatever. So this is simple capacitive touch screen, right? Capacitive pressure sensors basically work like that. How much has it deflected? And that depends on how much pressure or how much force is being applied on it. Now, depending on what kind of material it is, its deformation is related to the force which acts on it. And that's the correlation that tells you that what is the pressure on the other side which is deflecting it by so much. How much it is deflecting by, that we get from our capacitive sensing, right? So you get capacitors. So now, taking from there, you have all kinds of MEMS transducers that you can, these are all from my own research, and therefore, I'm just showing you a few examples. Gyroscopes, MEMS gyroscopes, MEMS ultrasound transducers. This is piezoelectric micro machined ultrasound transducers. I'll show you examples of this. I'll show you example of this. I'll show you examples of speakers. G switches. G switches are accelerometers, which are threshold accelerometers that, only if a particular level of acceleration is sensed by it, it engages like a switch here, okay? So this is used for triggering an event. That's what switches are for, right? Triggering an event that, hey, if you uh, sense a shock of 500 g, then do this, right? So if 500 g is the acceleration of something that this sensor here senses, then it latches here and it completes the switch, which could trigger another action. And that action could be, for example, G switches are very, very popular in in rockets, ballistics, that kind of stuff, where you have to detonate something once you know that it has hit a target, right? Now, suppose you are carrying a rocket, right, and you are loading it, and and you drop it by mistake, on the ground. It should not detonate just because you dropped it on the ground. That will be really dangerous. It should detonate only if it is fired and it hits a target, at that speed. Then the deceleration will be huge, and that deceleration is what it should sense as a threshold uh, deceleration or negative acceleration, and then engage the switch to detonate it. So these are also transducers of that nature. So let's look at all of these are MEMS transducers that I'm showing you. So what are basic MEMS transducer elements? Very simple structures are the elements of MEMS transducers. It could be a cantilever beam, which is very, very popular in MEMS technology, a membrane structure or a thin plate structure, or a planar ensemble of beams and plates. All of these are simple mechanical structures, right? So, if you think of a cantilever beam, it's like this. There is a cantilever beam. If you apply a load on it, it it deflects. And the deflection, delta is the load times length cube divided by 3 times Young's modulus and sectional inertia of this cross section. Right now, if you know this, that the force you applied and the deflection, they are related to each other in this form, then the force divided by the deflection gives you the stiffness, right? So you immediately can find out what the stiffness is. And if you know the stiffness and you know the mass, then its vibration characteristics, if it oscillates, you know its natural frequency of oscillation as well. These two quantities, stiffness or the deflection to an applied load and the frequency, these are enough to use a cantilever, a simple cantilever, in million ways in MEMS transducers, okay? Static, dynamic ways, and you can do all kinds of sensing. So MEMS cantilever beam might look like this. This is made in our facility. This is from the research of one of my students, where you build a U-beam kind of cantilever, and most of the times when you release it, there is some stress in it, because of which it deflects right in the beginning. Of course, you do all kinds of process optimization to not have that residual stress, so that it can be a flat cantilever. Nevertheless, you can build these kinds of cantilevers. How do you build them? I'll just show you a very quick, sort of canonical form of how they're made. Okay, I'm sure that you will have lectures on how these things are fabricated. But just to make sure, this is a cross-sectional view I'm showing you of a silicon wafer, right? So this is a silicon wafer, which is like a disc, say 4-inch silicon wafer. And imagine its cross-section you are looking at. When you take a silicon wafer, on the surface, it always has some native oxide, because it has been sitting there in the package, interacting with oxygen. You can clean the native oxide with RCA solution and DI water, and then you can deposit an oxide that it's uniform oxide deposited on it or grown on it with a kind of process that you have control over. So deposit oxide, silicon oxide, it could be thermal oxide, wet oxide, whatever. you wish. On top of that, let's do a photoresist coating. So photoresist, as you know, is a polymeric material. In solution form, you can easily drop it and spin it so that spreads, right? So you can spin coat the wafer with the photoresist layer. A thin photoresist layer is coated, and you have a mask. This is a quartz or glass mask that you have, in which you have certain opening. Let's say that we want to uh, pattern the silicon wafer such that I can make cantilever beam on it. Okay, that's what I'm trying to do here. So I have certain transparent region, okay, in the mask like this. And if I do UV exposure, then the UV will only go through here where the mask has transparency, and there the UV goes to the photoresist and reacts with the photoresist. Once it reacts, the bonds break there, and if I put it in a developer, then that part of the photoresist will be gone, right? So I have removed photoresist only from an area that I want to remove it from, a selected area. So photoresist is gone from there. Now, if I deposit uh, something else, some other material on top, like a polysilicon, it will be polysilicon will be going here as well. But before I do that, I removed the oxide layer. You remember that it was like this. Now I can use an etchant which loves the oxide but leaves alone photoresist and silicon. So I can use that and remove the oxide layer. Then I can strip the photoresist. And now if I deposit polysilicon on top, then polysilicon will be deposited as a layer on top, as well as in this groove that I made by removing the oxide from there. Now, if I remove the sacrificial oxide, then what I have is I have a free polysilicon beam sitting here, right? Which is anchored in this portion to the substrate. And that's how you get a cantilever beam. So this is a very old image from ITI, and I have kept it for historical purposes. This is done probably in 90 or something. Um, from ITI Bangalore, you can see that the anchor is right here, and this is the cantilever here, right? Just done by that process I described to you. So you can make these beams, you can make, plates like that, you can make structures which are beams and plates all put together, and we can excite them, we can measure their vibrations. We have a laser Doppler vibrometer that we use all the time for exciting these structures on the wafer and measuring their characteristics. So here is the cantilever beam, and I can excite it, and I can find its first mode of vibration, second mode of vibration, third mode of vibration. This is an experiment from 2007 that my very first student in MEMS did. Um, Professor Ashok Kumar Pandey, who is a professor now at IIT Hyderabad. So let's look at some MEMS sensors. Okay, here is an accelerometer structure. This is like a proof mass which is suspended, which is free to oscillate, and it is suspended by 4 beams. This is crab leg sort of beams. You can see, somewhat folded beams or swastika kind of beams, right? And the beam at the end is attached to the substrate, right? I mean, it's part of the substrate, and therefore it is anchored here. And below the plate there is free space. You have removed, you have etched material from there, and therefore this plate is free to oscillate up and down. A little bit more complicated structure will be this gyroscope, which has 2 proof masses. It has a comb drive here, comb drive here. This is a big plate you can see here. This is a plate with comb drives. This is another plate, but this plate is a fixed plate with comb drives. This is another just a replica of this proof mass here, and that also has comb drives. And this proof mass here is suspended by this beam, which is a folded beam like this, right? And this end is again with a beam which is folded like this, and these two proof masses are connected with a beam so that they're mechanically coupled. I'll show a bigger picture. Okay, so accelerometers, the kind of structure that I showed you here, different kinds of structures with comb drives are in here in the analog devices first accelerometer that came out. So the sensor element is right here. MEMS sensor is right here. The rest of it is all electronic components, for modulating, demodulating signals, you know, for timing, for power. You will have to have lots of other things that go with it, right? That structure that analog devices uses looks like this. This is the proof mass. These are folded beams which are anchored here. So if this proof mass oscillates up and down like this, these beams will flex, right? And if it moves like this, then these comb drives which are attached to it, the comb drives will also move along with this proof mass. And if there are fixed comb drives on, on the other side, these comb drives are fixed on this side. So then the comb drive which is with the proof mass, that is changing the distance between this particular comb drive comb or comb finger and this finger, and therefore you have a change in capacitance, and that's how you sense how much is this proof mass oscillating. And that's what is used in accelerometers. Now, you can build accelerometers which are dual axis accelerometers with all kinds of sophistication. This is done in our institute with Professor Anand Suresh's lab, where a mechanical amplifier, this is a mechanical amplifier which is used for amplifying the displacement, okay? In its full glory, you can see it here, fabricated structure. What does it look like, right? Similarly, the G switch that I showed you, that has a meandering beam like this so that you can provide enough flexure, right? You want it to be, this is like a spring which has low stiffness so that this can move, right? So if you want to make stiffness lower, then you want to increase the length of the beam. But if you just go linearly, if you increase it like this, then it is usually very hard to fabricate such structures and have reliability that they will hold good. Also, you will be using too much of real estate on silicon. So what you do is you fold them like this, okay? And that folded beam still gives you plenty of flexibility or flexure, right? For this to have the kind of flexibility you want for its motion. And then there are two beams here which can also flex, right? When this comes in, engages here, then these beams move tiny bit and let the key come in and then latch here. And once it is latched, then it is latched. That's it. That's the end of that motion. And that becomes a switch. Okay. So in the latched position, you can see it like this. So this is a G switch. And once you package it and stuff like that, it is right here. It's a 200 G switch. You can see here written Sense IISc. This was made at our center for one of our defense labs. Okay, so let me show you a gyroscope, right? So gyroscopes are transducers that measure angular rotation, right? The mechanical gyroscopes usually have a rotating spinning disc which spins at very high RPM, and its angular momentum is conserved. So if you apply any rotation on it, then its bearings in which this disc is rotating, those bearings experience incredible amount of force, and you can measure those forces. From those forces you can make out what is the rate of rotation. MEMS gyros are much smaller. These gyros, mechanical gyros, anywhere from 5 kgs to 5 tons. That you use those kinds of gyros on ships. But lightweight, very, very lightweight gyros now we make in MEMS technology. However, nature has even better designs. I won't have time to talk about that, but just to tell you that the gyros that we are making in MEMS, most of them are based on this effect called Coriolis effect. I'll show you how, and it turns out that the nature, the soldier flies use Halteus as their gyros, and they also work on Coriolis effect. So what is Coriolis effect? If you're sitting and if you throw the ball, it goes like that. But if you are rotating, and then if you want to throw to your partner, the ball doesn't go straight anymore. It just deflects and goes away, right? So it's not, the person is still trying to throw it to his friend. And it's because when you have linear motion in a rotating system, then there is uh, uh, an acceleration that results, if you do the math, it comes out very easily. Uh, uh, an acceleration that results because of this rotation, this linear velocity and the rotation combine to give you 2 omega cross v as the Coriolis acceleration. It's a cross product, and therefore it's perpendicular to both the rotation and the velocity. And that's why the ball is going where it is going, right? It is going away in that direction. So if you have linear motion, linear actuated motion, and perpendicular to that, if you have rotation, then you will have an acceleration working on it or acting on it, which will deflect the structure perpendicular to both these motions. So let's see how that works. You have here a proof mass, and these are elastic springs. The beams which are acting as springs. So you can actuate it by applying voltage to these comb drives. So notice here that the velocity, let's call this direction x, right? So your velocity is in the x direction of this mass, right? So this mass is moving in x direction, positive and negative x direction. Now, if you apply a rotation on it in the y direction, this is the y direction, in the plane still, in the y direction, then now you will have your velocity was in x direction, the rotation is in y direction. So you got your Coriolis acceleration, which will be in z direction, right? So now the same proof mass starts going up and down, as well as you are actuating it still, so it is going in x direction, but it starts going up and down. If it is going up and down, and if I have another electrode at the bottom of this plate, then I can use these two as parallel plate capacitors, and capacitance is changing, which is indicative of how much is the rotation. If I can get that change in capacitance, from which I can figure out what is the amplitude of this vertical motion, then I can figure out by back calculation what is omega, what is my rate of rotation. And that's what gyroscopes are for. So you can first design this MEMS gyro, in any of the many softwares that you have for design, CoventorWare or IntelliSuite or whatever you have. And then this is the fabricated structure, right? It's an optical image of having this proof mass, which is suspended by these beams, right? And beams are anchored at these places. And this other color you see that's the bottom electrode, right? That is at the bottom. And this is the electrode for this part, which is the fixed comb drive part. Okay. So you have your electrode pads where you can probe and apply voltage. If you look at scanning electron microscope picture, it looks like this. And this is the gyro that, we also have variants where these beams are more flexible. Um, but if you look at the comb drives, if you zoom in there, the comb drives look like this. You can see, these vertical walls, and the capacitance is between this and this, right? This and this. As well as if you look at fringe field, then the fringe field will be between this particular finger and this structure, which is all at the same voltage, right? So suppose that this is grounded and you have applied 5 volts on this, then you have now electric field between this and this, and there will be a fringe field which will pull this finger in this direction, right? So the whole structure will get pulled. So you can, I don't know if you can see on your screen that this structure here is actually moving, right? Um, both these proof masses are moving. The motion is very small, and therefore you may or may not be able to notice it. But I'll show you that if we make those beams slightly more flexible, then you can see far more motion, and it's clearly visible here. Even better is here that you can see we are just by applying voltage between this part and this part, we are able to actuate it and move it, right? So these gyros, we can put it in a vacuum chamber, because they're not yet packaged. Otherwise, you can package them in a vacuum packaging, and you can put them on a test bed where you apply a rate of rotation. The moment you apply a rate of rotation, you start seeing, the change in capacitance, and from there you can make out, how much is the rate of rotation. So by doing these kinds of experiments, we have here the input is rate of rotation here, and the output is change in voltage. You can see you can get a fairly good uh, gyro, right? That relates the rate of rotation to um, the voltage output. So this is this in packaged form looks like this. This is still an open package, but this is on a PCB, and this can be used. We are looking for packaging it in vacuum, and then this can be used as a normal gyro for all kinds of things. So this is for DRDO, for defense, and a similar one which is based on an angular or a ring gyro we have made. This is we have developed for ISRO. Okay, this is magnetic, this is capacitive, and this is electromagnetic. So there is a magnet here, and you use Lorentz forces for detecting the motion by change in current. Okay, in this one. Pressure transducers, you can make pressure transducers by having a membrane on which you can print piezoresistive piezoresistors. You can print them in Wheatstone bridge configuration. This is work done by my colleagues here, Professor Ken Bhatt and Professor M.M. Nayak, who made these pressure sensors for different ranges of pressure. And after fabrication, they look like this. Whenever pressure is coming from normal to this surface, okay, so pressure is applied, the membrane deflects, and once it deflects, there is strain here, right? And this is the strain in the piezoresistor strain that uh, unbalances your Wheatstone bridge, and by balancing it, you can figure out what is the strain there, and from there you can back calculate to know what the applied pressure is. So on a wafer, we make so many of these pressure sensors. You take one of them and you attach it, on a header. Then it looks like this. Do wire bonding, and after that you package it uh, and put it in a casing along with electronics. It becomes a product. It's a pressure transducer today, which is a really good product, which is commercially being now sold by a company to which we license the technology. and now HAL is using these sensors. Okay, so all the way from design to fabrication to testing to qualification to commercialization, we have done it all. Okay. Um, Another example I can give you um, is of micro speakers that we have built, MEMS speakers. Another transducer that we have built, and we built it by learning some tricks from crickets. These insect crickets. We were trying to studying these crickets, that how do they produce such loud sound just by moving their wings like that. All it is doing is moving its wings, and that's what makes this loud sound. They don't use vocal cords. They don't have vocal cords. So it's the wings that go in an angular sweep, right? Technically it's called stridulation, that kind of motion, and that's the motion that is creating this huge, or really um, huge amplitude of, or huge intensity of sound. But how does that work? If you look at the wings are going at 30 hertz. That you can't hear that. It's very low frequency, inaudible sound of the wing motion like this. But what you hear is high frequency and loud sound. So if you think like an engineer, that you have a system where there is input, which is this motion, and the output, which is this motion, what kind of transformation is taking place inside the system? What is the cricket doing? So we figured all of this out. Of course, I mean, ecologists have studied these systems, and uh, it's from them that we find out uh, how this whole thing works. So this wing, which the two wings go on top of each other, there is a plectrum, and there is a set of file of teeth here, okay, which looks like this. The set of teeth underneath this wing here looks like this. And then on the other side, there is a tissue on both. It's symmetric. So on there is a tissue here, which is called the plectrum. The plectrum goes over the set of teeth as the wings close, and that introduces impulses when it engages with each teeth and lives each tooth and leaves it, right? Then it pushes the tooth up. So one by one, the tooth are going up. So that is impulsive loading on the wing, and from those series of displacement impulses, uh, you excite a part of the wing which is called the harp. Harp is a thinner part of the wing, and that gets excited into resonance because its natural frequency is matched with the frequency of this impulse production. And that pushes this harp into resonance. And if it goes into resonance, then it will have a large amplitude motion. So that's your amplifier, or the uh, loudspeaker for the cricket, and that's how you get this motion, right? So what we did was we took measurements, we took photographs, put it in MATLAB, and build a model of this harp. Look at the set of teeth that it has. This is scanning electron microscope. How beautiful um, this is, and its features are in micron sizes, just like MEMS structures. And this is the plectrum here, right? So these are SEM pictures. Um, so from there, we built the model, and after building the model, we measured Young's modulus of the cricket wing, did a finite element model, very detailed model for boundary conditions. We studied that for 6 months to figure out what the boundary conditions are like. And once we excited it with the set of impulses, lo and behold, this is the kind of sound that you get from the finite element model, which sounds just like a cricket, right? So we did a lot of work on this, and we figured out how these crickets produce this sound. And then we figured that, okay, let's uh, take the clue from this design of nature and make MEMS speakers which are built on a similar principle, which is peripheral actuation. You don't have to excite it from the middle. All the uh, normal speakers that you have seen so far, all these electromagnetic speakers that we use, they all have a coil, in the center, right? A magnetic coil, and that's what pushes a membrane attached to the coil up and down when you send current through the coil, and that's what produces the sound, right? But what we did was we said, okay, crickets are able to excite this motion of the harp just from a side actuation. The set of teeth are just on one side. So we build speakers based on that principle where we have on the periphery here, this is where we have capacitive transduction, right? So you can see this top membrane, and you can see at the bottom it's only up to here, right? So the capacitance is between this and this. So it's peripheral, okay? A concentric electrode that you have, and then now you have, if you apply voltage between this and this, of course there is oxide in between, which is an insulator, so that this is not shorted with this. So if you apply voltage between this and this, there is force acting only here, and that pulls this membrane, right? And the membrane will oscillate because it has elastic properties, and you also have AC voltage applied on it. So by doing that, we can actuate this membrane, and that's what produces sound, right? So we have been able to design this, and now you have an absolutely thin speaker, right? Loudspeaker. So we can use it in earphone, maybe just a single transducer, you can use it in earphone, or a bunch of them we can use as an array in a headphone, or you can make arrays of arrays and use it as a picture frame speaker for inside the house as a singing frame. So we have been able to make these speakers. This is our patented speaker, and we are working on improving its performance. Right now, it's you can hear this is the sound recorded from our MEMS speakers. Okay, um, let's see. I think the, the flute you can hear very clearly from our speakers, or the sound from this instrument. This is all produced by the speaker, MEMS speakers. Okay, this is playing the sound of uh, clapping and cheering from the crowd on our speakers. So that's another transducer. Ultrasound transducers also we have made. Okay, these are piezoelectric micro machine ultrasound transducers. This is a stack of material where you have the structural backing, or the structural part of the of this PMUT is silicon. It could be just any kind of silicon, or silicon nitride also, or silicon oxide, anything you can have as a structural layer. That's the passive layer. And on top of that, so this is silicon here, this is silicon oxide. Then you have an electrode here, metallic electrode. We do generally titanium and platinum, about 150 nanometers. And you have PZT here, right? PZT is sol gel coated PZT here, and then another electrode. Either you can use gold or platinum or whatever you want as another electrode. So this is a stack of materials, right? Where you have one active layer of this piezoelectric material, right? So we are using lead zirconium titanate, or lead zirconate titanate, as your active layer, right? So this structure, when you want to build it, it will have all kinds of problems of interlayer stresses, which gives you a lot of headache in engineering. But that's what our job is, to engineer those layers and build structures. So if you apply voltage to that piezoelectric layer, then it produces certain bending moment on the structure, which makes it vibrate, right? So then you get vibrating uh, diaphragm, right? And the vibration will depend on what it's applied, what is the applied signal's frequency, right? You can vibrate it at its natural frequency. In that case, you will get resonance, and that's how generally ultrasound transducers are used at their resonance, so that you have a lot of displacement, okay, and you can produce louder sound. So this is how devices are fabricated. Here the two electrodes are not top and bottom electrodes, but right on top both the electrodes are there, okay, so that we can do actuation and sensing both from these two electrodes. So the bottom electrode and let's say that the middle electrode can be used for actuation, and the bottom electrode and this peripheral electrode can be used for sensing. So sensing and actuation both can be done from a single device. You can make gyro structures, you can make comb drives, you can make cantilever beams with the piezoelectric layer on top of it, so that you can build actuators out of them. So these all kinds of structures that we have been able to build for two-port resonators, and you can see that we can excite it, right, and we can measure its uh, motion just from the electrical sensing, which is coming from the piezoelectric layer. And you can see a resonance so clearly with the phase clearly visible. Okay, I have run out of time, so I'm just going to uh, rush through a few slides to show you that we indeed make a lot of these devices. You see here input voltage versus displacement of these diaphragms. These are the ultrasound transducers. Very nice result, very nice response. Um, this is a bulk transducer, ultrasound transducer, and the MEMS ultrasound transducer is sitting here. So this is just showing that, okay, it is able to sense the ultrasound waves from this transducer. Of course, this is like 6 years old result, and now we have much more sensitive ultrasound transducers. So we use these transducers as transmitters as well as receivers. That is a transmitter, and you can use it as a receiver here. Uh, this is put inside a box. This is a box, okay, inside the box, because we want to fill it up with fluids, and we want to do some experiments of PMUT, fluid PMUT. That means that at the bottom you have receiver, on the top you have transmitter, and the transmitter is transmitting the signal through the fluid. This is for density sensing. So this is how it is in actual setup. This is how it looks like. You can see here you have the transmitter and the receiver and the fluid in between. And when we do these experiments with different kinds of fluids, we vary the density. You can see a beautiful uh, reading through the change in frequency of these ultrasound transducers. You can sense density. Now, we would like to embed them in microfluidic channels so that we can pass fluids through the microfluidic channel and interrogate. We can interrogate the fluid. For example, blood for its red blood cells, and figure out whether these red blood cells are healthy, not healthy, or how many of them are there. These kinds of interrogation is possible by doing fluid spectroscopy. You can get the signatures, if you have a bunch of ultrasound transducers at the bottom, then you can get the signatures of the fluid and its constituents in the response of the ultrasound sensors, right? So we have built that. Here is the microfluidic channel, and here are the PMUTs. You can see a PMUT here, one here, and one here, 3 PMUTs, and microfluidic channel on top. We are doing experiments with this as of now to do spectroscopy. You can build an array of these. I'm working with Professor Rajsekhar Kotapalli at Penn State to do photoacoustic applications of these PMUTs, okay, where you have a laser in the middle, and with the laser you can excite very, very tiny organs in your body, and once they get excited with this thermal energy, they actually emit ultrasound waves, which can be picked up by these transducers here, these sensors here, ultrasound sensors here, and you can image where that particular part is, where that particular organelle rather is, and you can do imaging inside the body. So this is for vasculature. You can see you can get fairly detailed images by doing this. Okay, so with that, I would like to conclude. MEMS transducer technology is now spread out and ready for large-scale deployment and development. It fits the bill for inexpensive and extremely low power requirements of IoT. The area of application seems to be limitless. There are plenty of opportunities in design, development, materials, processes, systems, signal processing, and analytics. No matter which field you work in, you can contribute to this field of MEMS transducers. India is also making big strides in MEMS transducer development, as I showed you several examples of it. With that, an acknowledgement of my group of students, I thank the agencies, funding agencies, Ministry of Information Technology and IT, NPMAS program, which was DRDO, Office of Principal Scientific Advisor, MHRD, and DST for funding us where we have been able to do all this work. Thank you very much. I will be ready to take.
Participants, if any questions, please you can discuss.
Sir, may I ask a small question to you, sir?
Of course. Yes.
Go ahead.
Sir, in coating technology, in any type, this is a fine finishing process. Are there any? Then how this MEMS it will affect, sir?
Can you please
coating
repeat?
Coating technology and cutting tool.
Okay, coating technology in cutting tool. So MEMS technology is not for coating. Coatings are developed differently, but what we do is we experiment with lots of different coatings, as you saw, and that's why you are asking me this question, right? We are depositing different layers. So it's indirect effect because all these coatings, all these technologies that we are developing for coating surfaces, we do extensive characterization of these, right? So we can tell you that, okay, if we come across some material which has excellent, thermal properties or excellent, hardness properties, then we can tell you that, but and that can be used in, tools coating. However, MEMS technology is good for building transducers, right? That's where it has its strength. It can build transducers. So what we can do for you is we can build transducers which will monitor your coating, right?
Okay.
For example, I can have these very, very tiny ultrasound transducers that can keep monitoring the thickness of the coating on the tool, right? So while tool is working, every time you switch off the tool, the ultrasound device has to just send a pulse and get the reading back and tell you that, hey, your coating is intact or not intact, or is it getting damaged? That part is best done by MEMS technology.
Yes, sir. Thank you, sir.
You're welcome, sir.
Good afternoon, sir.
Yes, sir.
Sir, I have one question here, sir, regarding
Sure.
MEMS. Sir, in MEMS, we have seen that people normally use silicon-based materials for fabricating MEMS devices.
Yeah.
Are people also utilizing or exploring about organic materials for making organic MEMS or things like that? Or is it difficult to use organic materials for realizing MEMS devices?
Yes, yes. So, silicon is very popular because many of the technologies or the techniques that we use for patterning and for making these devices are borrowed from CMOS technology. So the origin is there, and that's why silicon has stuck. And it turns out that silicon is an excellent mechanical material. Therefore, it became very, very popular. But now there is so much of effort happening on using other materials. For example, I was showing you piezoelectric materials. You can use PVDF for piezoelectric materials. That's a polymer, right? That's not silicon. And it doesn't have to be on silicon either. So you can use all kinds of materials, and people are using now organic materials as well to make MEMS devices.
Thank you, sir. Thank you very much, sir.
So there was a
Your
comment. Yeah, go ahead.
So your
Excuse me,
student,
sir.
Dr. Suhas Mohite, has posted one thing. He was also one of the speaker in this FDP. He is on the board. He has mentioned that, sir, thanks. This is Suhas Mohite. Please tell about the journey till sense was built.
Yeah, so he was one of the pillars. Professor Mohite, he did his PhD with me, and he has seen uh, the struggles that we had when he was a student. We had no way of making devices at that point, so we used to design and send it to US. This was in 2000 up to 2010. That's what used to happen, right? So he was with me from 2003 or 4 till 2008, I think. For 4 years he was with me. So during those times, we had a MEMS lab, but all we had was design and characterization, testing. We had this vibrometer with which we used to uh, uh, do characterization of the devices. But we used to send our devices to US for fabrication. And it used to take 6 months for us to get back the device. And then once we'll get back the device, there will be some error, some fabrication problem, and it wouldn't work. It was very frustrating. Some of the senior people probably in this talk might recall that there was a time when computer programming used to be through cards, punched cards, and you punch these cards, 1,000 cards, and then you are in the queue in the computer center. You give it to them, and after 2 weeks, they will give it back to you, a printout which says that, okay, there is a comma missing on some do loop somewhere, and your program didn't run. It was like that you work for 6 months, send the design, and then your structure is not fully released. The beam is stuck somewhere in a corner, and then it doesn't work, right? So we went through that kind of development and pain for several years. And that's when, in 2002, I got determined that we have to set up a fab in the country to be able to work in this technology, and started working very hard with my colleagues here, Professor Naukant Bhatt, who had just joined in 99. With him and with some of the other colleagues, we built a team, and we worked extremely hard to make a proposal to principal scientific advisor, Professor Dr. Chidambaram at that point. And Dr. Chidambaram is the one who encouraged us to think that it is possible to make it. Till that time, everybody used to say that, no, you can't make it. It's too expensive. It's this, it's that, that kind of thing. And that was very, very discouraging. But Dr. Chidambaram encouraged us. He said, oh, give me a proposal, and I'll certainly take a look at it and see what can be done. So with IIT Bombay also had a team. They also had similar dreams. So these two teams got together and we gave a proposal. This is in 2003. We gave a proposal for 100 crores. You know, the two teams put together, 50 faculty members at IISc, 50 faculty members at IIT Bombay. And, 3 years later, uh, through so many hoops that I can't tell you. I mean, all of you have probably experienced of getting funding of, smaller amounts. And for that, we go through so many hoops. So this was 100 crores. You can imagine how many hoops we had, how many presentations, how many officers in Delhi we had to convince. It took us 3 years, but we did get 100 crores, 50 crores at IISc and 50 crores at IIT Bombay. At IISc, based on that 50 crores, we raised another 150 crores from various agencies, and IISc itself gave us a new building that I showed you right in the beginning. And that's how in 2010, we started construction of this new center called Center for Nanoscience and Engineering in 2006. And by 2010, the building was ready. And then in 1 year, we moved in, we built our clean room, and we moved all the equipment that we had got with that grant. And that's when, in all seriousness, the work started in 2012. 2011 was the movement year, making all the equipment and hookup and getting them to work. But from 2012, we have not looked back. Now, anything that you dream of making in MEMS, it can be made here. And the whole country is taking advantage of this. You can too. That's the story. Thank you, Professor Mohite, for asking me to elaborate on this.
Yeah, thank you, sir, for that. And one more question in the chat box by Professor Suresh Kumar S. Is there any technology to transfer electrical frequency into mechanical motion?
Yeah, the transducers, I just showed you that the ultrasound transducers do precisely that. They take electrical signal and they translate into mechanical motion. The membrane starts vibrating, and it vibrates at the frequency that the electrical signal is coming at. And that's how you transduce mechanical motion.
Okay. Any other questions from participants? So one more question in chat box you can refer to. Could we use the MEMS gyroscope in radar, lidar technology and in tanks or barrels of armaments?
Not quite. The frequencies that you need in the two systems have, for lidar or for radars, the frequencies that you use are very different. The MEMS gyroscopes, their frequencies are of the range of about tens of kilohertz. Okay, that's where we are. But these are two completely separate things. You make RF MEMS devices for radars, and of course that is done in our center. I don't work on RF MEMS, but there are other colleagues. Professor Saurabh Chandorkar is the RF MEMS guy who works on RF MEMS devices, and that's certainly used in what you are asking.
Okay, one more question in chat box, sir. What are limitations for it to use ultrasonic transducers?
What are the limitations? Well, see, this is a field which is developing right now, and it is developing rapidly. So we can't quite say that we have these limitations. Whenever we say that, that is only valid. That statement is valid for this year, because we haven't yet figured out something else to do. So, for example, right now, the ultrasound transducers that we have, in my lab, we go up to about 10 megahertz or so, 10, 20 megahertz. But, one of my colleagues at Cornell University, he has ultrasound transducers in gigahertz, right? So now the materials that we are using and the geometries we are using limits us to a few tens of megahertz. That's my limitation right now, because I'm looking at a different kind of application. It's not that we can't do the gigahertz ultrasound devices, but we are looking for something else. However, you do realize that these devices, these ultrasound transducers that I was showing you, they are very small. They are, 1 millimeter and below their diameter, right? All the way up to 50 micron diameter. So if such a tiny thing is vibrating, you can imagine that how much sound can it produce? How much energy can it pump in the air? It's not much. So if you want signal, ultrasound signal that goes from one building to another, it can't be done with this, right? But if you want a signal to go into very, very tiny places, like the vasculature study that I was trying to show you with photoacoustics, inside your body on an endoscope, you take it and you want to image one tissue, inside the tissue, if you want to image it, no other transducer can do it. This can do it. So everything has its own place and its own limitations, right?
Thank you, sir. And any more questions from the participant? Free to ask the questions. Okay, thank you, sir. So I will take a note of one of the participants' message mentioned in the chat box to thank you. That is your session was very enthusiastic and interesting. You gave us a different approach to think and learn from nature. Thought-provoking. Wonderful, sir. Thank you. Thank you very much. Thank you very much from SPC, sir. Thank you very much from all the participants. Thank you very much, sir.
Thank you for having me. It's just sad that you can't see all the people in front of you. As a teacher, as a professor, you are used to looking at faces and then.
Yes, correct, sir. I agree with you. Yes, sir. So, that's all we are missing. There are some advantages but some disadvantages it has.
That's true.
Yeah, thank you very much, sir. Once again, thank you.
My pleasure, sir. Thank you.